Alright, so suppose Bike Dude wants to visit his friend, so he zooms on over there. Vroom vroom. Hey dude, how's it going over here? We're toys, dude. We can't talk. If we want to know how far he went, we could grab a ruler and measure it. And of course, this is physics class, so we're going to use the metric system. So he went 24.5 centimeters. And that's cool, but suppose he'd done this instead. Vroom vroom. What's up, dude? Look, man, I told you, we're toys. We can't talk. We now have two how far did he go questions, both with different answers. The first question is how far is he from where he started? This is known as his displacement and it's a vector, so he is 24.5 centimeters that way. The second question is how far did he actually travel? And to answer that we need to take a measurement. Lucky for us, my ruler is bendy and this is easy to do. The distance he traveled is 30 centimeters. So you can see that distance and displacement are two different things. Distance is a scalar quantity that only has magnitude, where displacement is a vector quantity, so it has both magnitude and direction. Both are units of length, so are measured in meters or centimeters. And in Regents physics, both are represented by a lowercase d. In AP physics, however, we often use an x and sometimes a y. Most quantities are represented by a very specific variable, and distance, displacement are the major exceptions. If we're measuring a height, we might use h. If we're measuring a length, we might use l. This is a little annoying, but you'll get used to it. Now, to really drive home the difference between distance and displacement, let's have him go back to where he started. I will spare you the sound effects. Supposing he took the straight trip there and back, how far did he travel? If you said 49 centimeters, you're correct. But okay, what is his displacement? His total displacement at this point is 0 centimeters because he's right back where he started. Okay, so vectors and scalars can be similar but really mean different things. And just like we have the scalar distance and the vector displacement, the same is true with two words that you've probably always used interchangeably, and those are speed and velocity. They are actually different things. Speed is a scalar, which means how fast you're going. Velocity is a vector, which means how fast you're going in a particular direction. So you can ask yourself, is there a situation where you could have a changing velocity but not a changing speed? Is there a situation where you could have a changing speed but not a changing velocity? It turns out the answer to that second question is no. If you're changing speed, you're definitely changing velocity. But can you change velocity without changing speed? You can by changing direction. If you're going in a circle, if you're going around a corner, you can be at a constant speed, but not actually have a constant velocity. So calculating speed or velocity is very simple. You're going to take your how far quantity and divide by time, okay? So speed is distance divided by time, velocity is displacement divided by time. So let's take a look at our motorcycle guy and calculate his speed and his velocity at different points during his trip. In order to do that, we're going to have to do a little bookkeeping, and here it is. To get there, he went 24.5 centimeters in 2 seconds. He spent 1 second having a stupid conversation with his friend, and to get back, he went another 24.5 centimeters in 2 seconds. Or is that negative 24.5 centimeters? That's going to depend whether we're calculating velocity or speed. And either way, we're going to do that using the equation v equals d over t. For you AP kids, that's v equals x over t. So 24.5 centimeters divided by 2 seconds is 12.25 centimeters per second for the first leg of the trip. While he's not moving, his velocity is 0 centimeters per second. And his velocity on the way back is minus 12.25 centimeters per second. Let's label all of these velocities so that we can tell them apart. We physicists are fond of our subscripts. So what is his velocity from 0 seconds to 3 seconds? To get that, all we have to do is take his total distance traveled so far, 24.5 centimeters, and divide by the total time so far, 3 seconds. And that, of course, is 8.17 centimeters per second. What about his velocity and speed for the entire trip? His velocity, which we'll mark with this little arrow, has to be 0 centimeters per second, because his total displacement was 0 centimeters. His total speed, however, is the total distance of 49 centimeters divided by the total time of 5 seconds, or 9.8 centimeters per second. So there you go. Both quantities are calculated by dividing d over t. V equals d over t. So you're going to calculate them in a very similar way, but you have to take into account direction. For linear motion in this case, when we're just talking about back and forth, forward is positive, backward is negative. With displacement, that matters. With distance, it doesn't. If you have multiple legs of a trip, you just take the absolute value of each leg, add them all up, and divide by time. It is worth pointing out that in each case here we calculated the average velocity rather than the instantaneous velocity. The instantaneous velocity of our biker guy is going to change as he speeds up and slows down the whole way through. Whereas the average velocity is just going to be the total distance divided by total time, or total displacement divided by total time. Our final linear motion quantity is acceleration. And acceleration is often misunderstood. It is not how much your velocity has changed. It's how quickly your velocity has changed. So acceleration is calculated with a equals delta v over t. A is change in velocity divided by time. That's what this little delta triangle means. It means change. So a equals delta v over t. That's the definition of velocity. Now, calculating that is usually pretty easy, especially when we're dealing with an average acceleration. But suppose I tried to race Deputy Jaws. He's in his police cruiser and I'm in my Prius. If we had a race where who could go 100 meters the fastest, he's definitely going to win. He would probably have a greater acceleration and a greater average speed. If we had a slightly different race and we said who can get to 60 miles an hour faster, well, he's still going to win. But if we count the race from 0 to 60 miles per hour, we would both end up with the same average speed, 30 miles an hour, because 60 plus 0 divided by 2 is 30. But he would have done it faster, and so he would have a greater acceleration. So acceleration is not how much your speed changes. Acceleration is how fast your speed changes. And we'll definitely talk a lot more about that in class. One of the accelerations that is very commonly used in physics is the acceleration of free fall. If you drop something, if you drop pretty much anything, it's going to speed up as it falls. And it does so at a very close to the same rate all over the Earth. As long as you are near the surface of the Earth, that rate is 9.81 meters per second squared. So every second you fall, you're going about 10 meters per second faster than you were the second before. That's about 22 miles an hour. So after 1 second of fall, you're going 9.81 or 22 miles an hour. After 2 seconds of fall, you're going 9.81 more than that. You're going 19.62 meters per second, which is about 44 miles an hour. After the third second, you're going about 30 meters per second or 66 miles an hour and so forth. Every second, you're going that much faster than the second before because acceleration is how quickly your velocity is changing. There is no non-vector version of acceleration. Acceleration always has direction associated with it. So if you're driving forward and speeding up, you have positive acceleration. If you're driving backward and you're speeding up, you have negative acceleration. Where that might get a little confusing, if you're driving forward and you hit the brakes, you have negative acceleration. Your velocity is positive, but your change in velocity is negative. You're slowing down. So technically, your brakes are an accelerator. Because acceleration is a vector, when you change your velocity with the steering wheel, you're also technically accelerating even if you're not changing speed. So we call the gas pedal in a car an accelerator, but technically the brakes are also an accelerator and so is the steering wheel. But don't call them that in front of your mechanic because you'll just annoy and confuse them. Okay, so we have distance and displacement, we have speed and velocity, and we have acceleration. Those are all the quantities you need to know. In our next video, we're going to look at graphs of motion and how we can use a very simplified version of calculus to come up with some of the equations you need to know, and also introduce you to the idea of doing something new with graphs that you haven't had to do in the past. All right? Stay tuned.